Hi students, welcome to another video on the chapter on metals. Today we are going to continue with the second part, which is on the reactivity series of metals. In the previous lesson, we saw the part on metals as well as alloys, with the main concept being pure metals, they are very soft, and in light of that, it does not give us very good properties for us to manufacture products and items that we use in daily life. For instance, things like your tables and chairs and so on, right? So most of the metals that we use are in the form of alloys, where alloys are a mixture of metals with one or a few other elements in it, so that we can modify the physical properties a bit to make it harder, to make it a bit stronger, and sometimes also to improve the appearance, lower the melting point, and so on, so that we can use it for a wider range of purposes. Alright, so in today's lesson, we're going to look at reactivity of these metals. So if you look at the periodic table, by now we should all know that metals, they generally lie on the left hand side of the periodic table, whereas elements on the right hand side, they are more non-metallic. Okay, and another piece of concept that we should bring into this chapter will be that the part on atomic structure and chemical bonding. Okay, so using the example of our good friend sodium, right? In the topic on atomic structure, we have mentioned that for instance, sodium atom, it has the electronic configuration of 2.8.1, so it is not very happy being in this position. It wants to achieve the stable octet electronic configuration. So what does sodium do? It will then lose this valence electron in order to form the sodium cation Na+, so that it is 2.8. Then for magnesium metal, which is Mg, it has electronic configuration of 2.8.2. So in this case, magnesium will want to lose 2 valence electrons in order to form Mg2+ ion. So you notice over here that we mentioned that chemical reactions and chemical properties are very closely linked to how readily your metals are able to lose the electrons, right? So just looking at the example of sodium and magnesium alone, you should be able to deduce that magnesium metal is very likely going to be a bit less reactive than sodium, right? Because of the very fact that it has to lose 2 valence electron. It is almost like a extra step that magnesium has to take in order to fully react. Okay, so yes, coming back to the main point, for this particular lesson on part 2, the reactivity series, we will look at how the different metals have different reactivity. They will behave differently in their reactions with water as well as steam, and then also their reaction with dilute hydrochloric acid. Okay, so just keep in mind also this concept from the topic of periodic table. We mentioned that the elements are grouped in such a manner in the periodic table for a reason. For instance, when we learned the group 1 metals, we saw that the very fact that group 1 elements, the alkali metals, they have 1 valence electron, it also means that they have similar chemical properties. So we saw that the alkali metals, they behave in a similar way when they react with cold water, right? Remember, alkali metal reacting with water will form metal hydroxide plus hydrogen gas. Okay, so keep this in mind, that the number of valence electrons determines the chemical properties. So all these will come in handy when we look at this part of the chapter in greater detail. Okay, let's jump straight into it. So the reactivity series of metals that you are required to know for your O level as well as N level will be this. Okay, so starting with potassium and then ending with silver. or gold sometimes. Okay, so in the reactivity series, your metals are arranged from the most reactive to the least reactive. So the most reactive here being potassium, so it is placed on top from the most reactive all the way down to the least reactive, in this case silver. So you must be wondering how the reactivity series of metal was obtained, right? How do we know that potassium for sure is right at the top and then silver on the other hand is all the way at the bottom? Okay, so the simple answer to this is that scientists, when they first wanted to rank the reactivity of metals, they had to trial and error and test out and find out how they react with certain things. So in determining the order of reactivity of metals, it can be done by comparing their reaction with water as well as steam. So steam basically is just water, but there's more energy being given to it water being in the liquid state, whereas steam is water in the gaseous state. Okay, and then for certain metals where their reactivity cannot be determined by reacting with water and steam, then it can be further differentiated using a stronger or harsher kind of material reactant, which is dilute hydrochloric acid. Okay, so let me quickly just bring you back to memory of this lesson that we had on periodic table, right? Okay, so on the physical properties of alkali metals. So we have previously seen this experiment before, correct? So we have cold water, and then we have the group 1 alkali metals, namely lithium, sodium, as well as potassium. So we have already seen how these 3 different metals will react differently when placed into water. Okay, so if you want, I can also link the video up there somewhere in this video so that you can click on it and review that chapter if you so wish to. If not, then let's look at the first type of reaction, which is reaction of metals with cold water, which again, as I mentioned, is what you have seen in the topic of periodic table. So this is quite just a repeat. So some metals react with cold water, and the products that they form are a metal hydroxide as well as hydrogen gas. So to represent this type of reactions in a word equation, it will be as follows. So metal plus water, and then you indicate with an arrow which represents the progress of the reaction to form your products, which are a metal hydroxide plus hydrogen gas. Okay, so just a note on chemical equations at this point, right? So my general advice is always just write out the word equation first, and then so that you have a structure to follow. Then after that, based on what the question gives you, then you write the chemical equation and use the appropriate chemical formula accordingly. And then of course you balance the chemical equation plus you write the state symbol. Okay, so in this type of reactions, so reaction with cold water, right, a more reactive metal will therefore react more violently with cold water. So just like the video that we saw in the previous chapter, potassium being the more, or rather the most reactive metal out of the 3, which is lithium, sodium and potassium, it will then be observed to react more violently. As we have seen, it will immediately produce a flame, whereas sodium is less vigorous than that, and then lithium is kind of a bit more boring in that sense. It doesn't react that well. So if we have a look at this right now, this table is a summary of the observations as well as the equation for the reaction of the following metals together with cold water. So this table, okay, so it's found on the next page of your notes. Likewise, it's also found in your textbook. So for instance, let's look at potassium, right? So again, why is potassium found right at the top of the reactivity series? Because when we place a tiny piece of potassium metal in cold water, so again, cold water, right, it's just water from the tap, it already is able to react very violently to form potassium hydroxide as well as hydrogen gas. So enough heat is actually produced to cause the hydrogen gas to catch fire and explode, right? So one of the properties of hydrogen gas is that it's very flammable. So as a result, that's the main reason why in the experiment that we saw in the previous video, you saw that when potassium is placed in the water, immediately there's a flame, it catches fire, okay? Because the product, one of the products, which is hydrogen gas, is being ignited by a lot of heat that's being produced. Alright, so this is what we call it an exothermic reaction. This type of reaction we will learn in Sec 4, but it's not difficult to understand. Exothermic, exo means exit, thermic means thermal. Thermal is just another word for heat, right? So exothermic reactions are reactions that generate heat. So when we go to Sec 4, we will come back to this again, and you should be able to fully appreciate this particular reaction. Next, we look at sodium. So sodium is further down the reactivity series, so we would also therefore expect it to not be as reactive as potassium. And true enough, when placed in cold water, sodium reacts violently to form sodium hydroxide and hydrogen gas. And so on and so forth. So as you can see, right, so when it goes to calcium, it reacts readily. Moving to magnesium, it then starts to react very slowly to give magnesium hydroxide and hydrogen gas. So in fact, if you want to collect a full test tube of hydrogen gas, it can only be produced if you let the reaction run after a few days. Okay, so this really illustrates that as you go down the reactivity series of metal, your metals do not react that well anymore. In fact, to the point where once you reach zinc and beyond, right, iron, lead, copper, silver, there is no reaction that occurs. So then for zinc onwards, right, because the use of cold water can no longer help us determine the relative reactivity, the next best way will be to react it with steam. So in order to produce steam, we need to give it more energy, right? We need to heat the water in order for it to change from the liquid state to the gaseous state. Which brings me to my next point. The second type of reaction will be the reaction of metals with steam. So back to what I was saying. So zinc and iron, they do not react with cold water, but we will be able to find out their relative reactivity by reacting them with steam. So the word equation here will be metal plus steam to give us metal oxide plus hydrogen gas. So similar to the previous reaction, a more reactive metal will also react more violently with steam. The experimental setup for the reaction of metals with steam is as follows. So as you can see, there will be this boiling tube that is arranged in such a manner with a glass wool soaked in water on one end, and then you have the metal sitting in the middle, and the heat source, which is from the Bunsen burner, is directly below it. It is also connected via a delivery tube towards this setup over here, which is the downward displacement of water. So this should be quite familiar to you as well in our I think it's second chapter on measurement and experimental techniques, right? So here, because one of the products produced is hydrogen gas, so if I want to collect hydrogen gas, then downward displacement of water is one possible way, because hydrogen gas is insoluble in water, right? Remember, because hydrogen gas is a covalent molecule, so one of the physical properties is that it is insoluble in water. Okay, so just a side note, just from this alone, you can see that many of the concepts in earlier chapters are coming together, informing your understanding for subsequent chapters. So yeah, please be reminded to not forget things that we have learned from the start of the year. Okay, so in this experiment, your metal will be strongly heated. So the water that is soaked in the glass wool is likewise being heated in the process to generate a flow of steam, which is water in the gaseous state, over the hot metal. So this is how the reaction is able to happen. So back to the table that we were looking at earlier on. Now let's look at the second column, which is the observations and equation for the reaction of the metal with steam. So notice that again, for the first three metals, which we have already established that they are very reactive, you'll notice that this reaction with steam, we do not carry this out in the school lab because they just are so reactive that the reaction is very explosive. Okay, so it's very dangerous. Let's look at how the other observations are like for the subsequent metals. So for magnesium, hot magnesium will react violently with steam to form magnesium oxide, which you will observe to be a white solid as well as hydrogen gas. You'll also notice that there is a bright white glow produced during the reaction. Then moving on to zinc and beyond, right? So as you can see previously, when we react zinc and the subsequent metals with cold water, no reaction occurs. But this time around, when we react with steam, we can then further differentiate the relative reactivity. So for zinc, you notice that hot zinc reacts readily with steam to produce zinc oxide and hydrogen gas. You'll also notice that the product zinc oxide is yellow when it is hot, and then if you leave it to cool down, after a while you'll notice a change from yellow color to white color. So zinc oxide, when it is cold, it is white in color. Iron, right, it will react very slowly with steam to form iron oxide and hydrogen gas, and you will also be able to tell that iron is less reactive than zinc because the iron must be heated constantly in order for the reaction to proceed. Finally, you look at the next part, right, which is, or rather the next few metals that are below zinc and iron. We have lead, copper and silver. Again, we have the same issue coming up where if you react these three metals with steam, we do not see any reaction. So again, we need another reactant which is able to further differentiate the three metals in terms of reactivity. So that would be hydrochloric acid. So this is the third reaction of the metals with dilute hydrochloric acid. When a metal reacts with dilute hydrochloric acid, the products are a metal chloride, which in a subsequent chapter we will delve into it a bit more. These are actually known as salts, okay, and then also hydrogen gas. So the word equation will be metal plus dilute hydrochloric acid to give us metal chloride plus hydrogen gas. The reactions of different metals with dilute hydrochloric acid will again indicate how reactive the metals are. A more reactive metal will definitely react more violently. So again, another table to summarize the different observations as well as the corresponding equation. So looking at the first few metals, potassium and sodium, it for sure will react very explosively. This is super dangerous and should not be carried out in a normal school laboratory. Calcium, it will react very violently. Magnesium reacts rapidly. Zinc will react moderately fast. Iron reacts very slowly. Okay, so looking at our three metals right at the bottom, lead, copper as well as silver, you'll notice that even though we now change the reactant from water to steam and then finally now dilute hydrochloric acid, right? So acids are pretty strong. You notice that these metals don't even react with acid. Okay, so this gives you a very good indication that these metals, they are really not very reactive. They are unreactive. Okay, so based on the reactions that we have seen so far of metals reacting with cold water, steam as well as dilute hydrochloric acid, we can then be able to place these metals in order of their relative reactivity, right? So again, the reactivity series of metals, we basically place the metals from the most reactive to the least reactive. And at the start of this video, I've also shown you what it is. So potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, hydrogen, copper, and then silver, right? So and as mentioned, you have to know this reactivity series by heart for the O levels as well as the N levels. So just by looking at this plainly, it is very difficult to remember. So it will be helpful to help yourself to use mnemonics to help you remember this reactivity series. Okay, so this is what I used as a student when I did my own O levels when I was in secondary school, and I found this very helpful, so I will share with you. So you can remember in this way. So please stop calling me a zombie, and then I love hot chicken soup. Alright, so in the exam or when you're doing your worksheets, you can just chant this to yourself. Please stop calling me a zombie, I love hot chicken soup. And then write out the corresponding metal that it stands for, and that should help you to recall the reactivity series and answer the questions accordingly. Just a note that I wanted to make on this part on hydrogen. Okay, so you should, just now when I read this out, you should wonder how come hydrogen is here. If not, then it shows that you are not paying quite close attention, because hydrogen, as we know, hydrogen gas is a non-metal. So the question is, why is hydrogen in this list, right? A simple explanation will be that hydrogen, remember hydrogen, the electronic configuration is 1, right? So in order to become stable, hydrogen can form the H plus ion, which is the main component of acids, which is our next chapter. So H plus ions, right? And how do H plus ions get, or rather, how do the hydrogen atom form H plus ions? It is through the losing of that one electron. Okay, so with that kind of behavior, that grants hydrogen a rather similar behavior to your metals, right? Your metals, such as, let's say, sodium, our good friend, you will lose that one valence electron in order to form the sodium ion, for instance. Okay, so in terms of behavior, it's somewhat similar to the metals. So hydrogen is placed in this reactivity series as a guide, so to speak. Okay. Just one more note that I just wanted to highlight for you to appreciate things a bit better. Notice that the reactivity series of metals, the first few elements, namely potassium as well as sodium, these two are on top, right? So meaning they are the most reactive of this bunch. Notice that these two elements, they are in group 1 of the periodic table, meaning they only need to lose one valence electron, right? Which is easy. Compared to let's say calcium and magnesium, which is from group 2, now they have another one more valence electron to lose, right? Which is it has a higher barrier, which is why logically they are now a bit less reactive than that of our group 1 metals. That's why they are placed below potassium as well as sodium, and so on and so forth. Okay, aluminium is in group 3, and then subsequently all these are transition metals, which is not quite in your syllabus for O and N levels, but again, if we go by periodic trends, that is something that you should be able to appreciate even without understanding the deeper reasoning. Okay, moving on to the final part of this segment on the reactivity series, we'll be talking about what are some of the usual questions that will tend to be asked for this portion. So basically you'll be mainly using the reactivity series to deduce the order of reactivity of metals. So you can use it for mainly two purposes. So number one, to predict the reactivity of a metal from its position in the reactivity series, which is the simpler part. The more challenging part that comes out in application questions will be to predict the position of an unfamiliar metal in the reactivity series from a given set of experimental results. So meaning to say, for instance, platinum is a metal that is not in the reactivity series, but questions will tell you things like, oh, platinum, when it's placed in hydrochloric acid, there is no reaction, okay, and so on and so forth. So it will give you a set of experimental results, some data here and there, and then based on the data as well as experimental results, you are supposed to predict where does the unknown element, or in this case, where does platinum lie in the reactivity series, something like that. Okay, so for the next part, can you just spend some time to do the 2 questions under this portion on try it yourself. You can pause this video to do the questions, and then you can press play and I will go through the answers. Okay, so let's assume that you have done the 2 questions and you are not just waiting for me to give you the answers. Let's look at question 1. Here you have 4 different setups where different metals were added to dilute sulfuric acid. Question asks you, in which beaker will a reaction not take place? Okay, so this is corresponding to the first type of questions that you'll be asked, right? Predicting the position of where the metal lies in the reactivity series. Okay, so this kind of question is very simple. So as long as you are able to remember and regurgitate the reactivity series of metals, which I've already taught you the easy way to remember, right? So yeah, so again, chant to yourself, please stop calling me a zombie, I love hot chicken soup. Okay, write this at the side, and then if we look at the options here, so A is copper, right? So copper is here, right at the bottom. Iron is here, magnesium is here, and then zinc is here. So as we know, the reactivity series of metal is from the most reactive metal to the least reactive metal, right? So question asks you, which beaker will reaction not take place? Then definitely it has to be the one that is the lowest, or rather at the most bottom of the series. So in this case it will be C, which is copper. So answer is A. Question 2, they give you 5 metals, A, B, C, D, E. So these are unknowns, right? You have no idea what this corresponds to, the actual identity of the metal. Okay, these were investigated and the results recorded in the table below. So this kind of question is also quite common, right? So give you the unknown metal. They don't tell you the identity, but they will tell you what are some of the properties as well as what are the observations when these metals are placed into cold water, steam, as well as dilute acid. Okay, so you have all these properties, and then question asks you to arrange the metals A, B, C, D, and E in order of their reactivity from most reactive to least reactive. So this kind of question is where you need to be able to appreciate and understand their relative reactivity based on how they react with these 3 substances. Okay, so the first reaction is cold water, right? So if I see, let's say, metal C, okay, it's able to float on water and it reacts very vigorously with it. So if I see this kind of observations, then surely I know that metal C is very high up in the reactivity series. Okay, so in this case, most reactive metal is metal C. Then next, I would want to look for metals that can also react with water, but maybe less readily than metal C. Okay, so in which case will be metal B. It sinks in cold water and reacts, it still reacts, right? Though not vigorously, alright, to produce your bubbles of hydrogen gas. And then when you put it into dilute acid, it's able to react violently. Okay, so this indicates to me that B is still indeed quite a reactive metal. So next one is B. Then the rest, you notice that they cannot react with cold water. Alright, so then the next thing we check will be the second reaction, whether it reacts with steam or not. So we have metals A and E, which can react with steam, but notice that metal A, it will burn in steam, but metal E, it will just react with steam. So can you see that it's a bit of English right there? So if metal A is able to burn, so it shows that it is relatively more reactive than metal E. So we'll place A first, then E, then finally it will be metal D lah, because it cannot even react with steam or dilute acids. So this probably indicates to you that metal D is maybe lead, copper, silver, or gold, something like that. Okay, so yeah, that is it. So this is the end of our second part of this chapter, which is on the reactivity series of metals. In the next part, we'll be talking about how we can extract metals in order to, in the next step, we can then make good use of these metals as raw materials for, again, manufacturing of items that we need in daily life, or for other chemical reactions, and so on and so forth. Okay, so hopefully this video has been a fruitful one for your learning. If there's any questions, we'll see you back in class and we will clarify them as well as to do more questions. Goodbye.